Hello everyone, welcome to my channel, The Teaching Show. Please like, subscribe and press the bell icon for more updates. So we are right now seeing various problems on thermodynamics. So this is again a video in the same series. I will be taking three more problems in this video. So let's get started. So now we have a problem in which we want to find out what is the heat transfer or heat which is lost when a turbine is generating work W, and how the turbine is generating work. A steam at high pressure, it is entering the turbine, producing some shaft work and leaving at a low pressure. Okay, so the mass flow rate of steam is 26 kg per second, and the inlet pressure is 6 megapascal, and it is coming at 600 degrees centigrade. Initially, we are assuming that the velocity of steam is negligible. The outlet conditions have been given as pressure is 0.5 megapascal and the temperature is 200 degrees centigrade, plus the velocity of the outlet stream is 180 meter per second. Okay. Further, they say that neglect the elevation change. So elevation change is neglected. That means the potential energy change is neglected. So the turbine inlet and exit elevation change is negligible, and we are required to find out what is the amount of Q which is lost in this process, given that W is equal to 20 megawatt. Okay, so let's tackle this problem. First of all, we are going to write steady state energy balance. So for an open system or for a control volume, when you apply your first law to a control volume, you get this type of equation, which is change in enthalpy plus change in kinetic energy plus change in potential energy, which is neglected, that is equal to work done plus heat exchanged. Okay, so in this equation, let's see what are the knowns and what are the unknowns. So H2 we don't know, H1 we don't know, mass flow rate we know, it is 26 kg per second, fine. Velocity at the outlet is given, velocity at the inlet we are assuming it to be 0, W is given 20 megawatt, and Q needs to be calculated. So we are going to use this equation to calculate Q, but in order to find out Q, you must first calculate H2 and H1 and then the problem is easy. Okay, so let's first find out what is the enthalpy of the inlet stream. So at inlet, your pressure is 6 megapascal. So where do we go to find out its enthalpy? Of course, we will go to saturated steam table first. Let's go and check the saturated steam table. If you do that, you will find that for 6 megapascal, saturation temperature is 275.58 degrees centigrade, which is much lower than the inlet temperature of the steam. What does it suggest? It suggests that your steam is superheated. What is the degree of superheat for this steam? It's very simple. You just subtract 600 minus 275.58, and whatever that it comes out to be, it comes out to be about approximately 324.4 degrees. So that is your degree of superheat. Okay, so now you have found out that the steam is superheated. So now you have to go to superheated steam table. So let's go to superheated steam table corresponding to 6 megapascal, and then you from the table you locate the temperature 600 degrees centigrade. So I will go to a superheated steam table corresponding to 6 megapascal, locate the temperature 600 degrees centigrade, and then from there you read the enthalpy of that steam. So it comes out to be 3658.7 kilojoules per kg. Okay, so now we have calculated what is H1. Let's now find out what is H2, that is the enthalpy of the exit stream. So how do we calculate it? Let's again go back to the saturated steam table. It is given that the pressure at the outlet is 0.5 megapascal. When you look at this saturated steam table, what you find is that corresponding to this pressure, the saturation temperature is 151.83 degrees centigrade. But what is happening? Your steam which is coming out of the turbine is at 200 degrees centigrade. So again you find that your steam is superheated at the exit also. What is the degree of superheat? It is 200 minus 151.83. So you find out what is the degree of superheat of the outcoming steam. Okay. Now, once we have found that this is a superheated steam, I will again go back to superheated steam table. Corresponding to a pressure of 0.5 megapascal, I will go and locate the temperature that is equal to 200 degrees centigrade. Once I have found out this entry, then I will go and read the enthalpy directly from the superheated steam table. So now it comes out to be 2855.8 kilojoules per kg. So now I have read H1 and H2 from the superheated steam tables. Now I can put everything in this equation to calculate Q. So m dot is 26 kg per second, H2 is this value, H1 is this value, P2 square is 180 ka whole square, V1 square, V1 is taken to be negligible, W is 20,000 kilojoules per second. So putting all these values in energy balance, we get the value of Q as 457 kilojoules per second. Okay, next let's proceed to problem number 8. Problem number 8 is a hollow spherical iron container whose outside diameter is 40 centimeter and the thickness of this container is 0.4 centimeter. So this thickness is 0.4 centimeter. Now this spherical container is filled with ice and water which is maintained at 0 degree. If the outer surface is at a temperature of 3 degrees centigrade, then this question asks you to determine the approximate rate of heat loss from the sphere, or whatever the heat is coming inside the sphere, and the rate at which the ice is melting in the container. The given data is that the conductivity of iron is 80.2 watt per meter per degree centigrade, and the heat of fusion of water. What is heat of fusion? It is the latent heat which is required to convert 1 kg of ice to 1 kg of water. So the amount of heat which is required to convert 1 kg of ice to 1 kg of water is 333.7 kilojoules per kg. Okay, so we have to make following assumptions. First of all, it's a steady state conditions. Then the inner wall, it always remains at 0 degree centigrade. It's a fair assumption because inside there is ice in equilibrium with water. So the temperature will always be 0 degree centigrade. Outside temperature, we are assuming that it remains at 3 degree centigrade all the time. Now further we are assuming that heat transfer through the shell is one dimensional and the thermal properties of iron shell are constant. Okay, one main assumption which we are making now in order to tackle this problem is that we are assuming that a spherical shell is approximated now as a plane wall with a thickness of 0.4 centimeter. And when we are making this approximation, what we are assuming that this plane wall has the same surface area as that of a spherical shell. So what is the area of the spherical shell? The curved surface area of the spherical shell, it is calculated over here. So the area is equal to 0.5027 meter square. So now we are we will use just this area and we will assume this spherical shell, or approximate this spherical shell as a plane wall, okay, of area 0.5027 meter square and a thickness of 0.4 centimeter. Now let's apply this well-known formula. You all have studied or might have studied heat transfer. So the heat flux Q by A, that is equal to K into delta T by L. L is the thickness of the wall, which is equal to 0.004 meters. It's given that it's 0.4 centimeter. So converting it into meters, the temperature difference across the wall is 3. The area we have calculated as 0.5027 and the thermal conductivity is given as 80.2. Putting everything in the equation, we get the heat which is lost, that is equal to 30.2 kilojoules per second. Now the rate at which ice melts is given by this formula. From where does this formula come? Q is the heat which is leaking inside this container. So 30.235 kilojoules of heat is leaking, and we know that about 333.7 kilojoules of heat is required to convert 1 kg of ice to 1 kg of water. So we are just dividing the heat which is coming inside or which is leaking inside the container divided by the heat of fusion. So it will give you the mass of ice which melts. Okay, so now the rate at which ice melts is given by this, and it comes out to be 0.0906 kg per second. Fine. Now let's proceed to the third problem. This problem says that we have a water pump. It consumes 2 kilowatt of electric power when operating. It is claimed that this pump can be used to lift water from a lake and pump it to a pool which is 30 meters above the free surface of the lake. Okay, and the rate at which it delivers water, it is 50 liters per second. Now you have been asked to determine if this claim is reasonable or not. You have to find out whether this is false or true statement. Okay, in order to solve this problem, we will make some assumptions. First of all, we will say that the change in flow energy is negligible. Okay, so whatever the PV work which is done, let's say it is negligible. Further, we are assuming that this pump, it is just lifting the water, so it's not increasing the velocity of the water that much. Okay, so we are going to take the change in kinetic energy as negligible. Further, we will assume that the heat loss is also negligible. So when we put all these assumptions in the energy balance, what we get is that work done, that is equal to mg into Z2 minus Z1, where Z2 minus Z1 is the change in the datum level, and how much it is? It is 30 meters. Okay, so Z2 minus Z1 is 30 meters. M dot, that is the mass flow rate we have to find. We have been given volumetric flow rate. So if I multiply this with the density, then I will get what is mass flow rate. So I am just multiplying the volumetric flow rate by the density to get the mass flow rate, which comes out to be 50 kg per second. So now plugging this in equation, I get the work which is required to lift 50 kg per second of water to a height of 30 meters is about 14.7 kilowatt. Now this power which is required is much larger than the power of the pump which we are using. Okay, so whatever the claim which has been made that this pump is used to lift water 30 meters above the free surface of the lake, this is false. Okay, so now I end this video, and thanks for watching. Please leave any comments if you have any suggestions, and please subscribe to the channel. Thanks for watching.